from University of Chicago. So Dr. Guha is the director of the Nanoscience and Technology Division and the Center of Nanoscale Materials at the Argonne National Laboratory and a professor at the Institute of Molecular Engineering at the University of Chicago. Dr. Guha came to Argonne in 2015 after spending 20 years at IBM Research, where he last served as the Director of Physical Sciences. At IBM, Dr. Guha pioneered the materials research that led to IBM's high dielectric constant metal grade transistor, one of the most significant developments in the silicon microelectronics technology. He was also responsible for initiating or significantly expanding IBM's R&D programs in silicon photonics, quantum computing, sensor-based cyber-physical systems, and photovoltaics. Dr. Guha is also a member of National Academy of Engineering and a fellow of the Materials Research Society, American Physical Society, and the recipient of 2015 Prize for Industrial Application of Physics. He received his PhD in material science in 1991 from the University of Southern California and a BTech in 1985 from the Indian Institute of Technology, Kharagpur. At Argonne, his interests are focused on discovery science in the area of nanoscale material for energy, sensing, and future information processing, and their translation to applications. So I welcome Dr. Guha. Please come.
Okay, thank you for the introduction, Priyanka, and thank you for inviting me here to speak. So I'll keep it very informal. Please ask me any questions if you have any questions. But I'll talk to you about some work we have been doing at the University of Chicago and also here in India. This work is funded by the Gates Foundation, now Tata Foundation, and these are all my collaborators. How many of you have heard of the word, because there are a lot of students here, Internet of Things? Just raise your hands. Okay, good. So another word for Internet of Things is basically cyber-physical systems, right? What is it? Think of a lot of sensors. They could be sensors for air, water, land, doesn't matter. And these sensors are all connected either wirelessly through cell connections, wireless system connections, wires, to a central, cloud computing system. So all of the data comes over there. And over here, you use all of the data and physics, chemistry, mathematical models to come up with new predictions. And those predictions form new data layers. And then you can then send that data down to your customers, who could be farmers, if this is agriculture, it could be environmentalists, if this is to do with environment, etc., right? So this whole thing is called a cyber-physical system. And you have one curation platform, and you can change your sensors like light bulbs in and out. Right? It's like, Amazon.com. You can buy books, you can buy clothes, but it is one business platform. Right? So this is sort of the future of cyber-physical systems, Internet of Things, etc. Now, this whole business of Internet of Things is limited today by the quality and the price and the efficiency of the sensors. And this is the big thing that will happen in the next 5 to 10 years when the sensing technologies in any of these fields that we want to do, right? When the price will reduce. Okay? So this is an area I've been working on from the time I was in IBM. And it is only in the past 5 years or so that all of the technology elements have come together so that these systems can be put together without requiring extreme specialist knowledge. And this is what we've tried to do, and I'll show you 3 examples, one in agriculture, one in environment and soil, and one in water. I'll probably spend more time on the one in water because that seems to be of interest at ATREE. And again, if you have any questions, just stop me and ask. So in agriculture, for instance, agriculture is the one field that has not been fundamentally altered by big data, by advances in computing. Almost every other big business has been reshaped by computing advances. Agriculture, not as much. But if you look at the amount of water, the amount of fertilizer that is added in agriculture, it is overused by factors of, people estimate, 2 to 5. Because you have too much fertilizer, you have a lot of nitrates, that goes off in the runoff, that then pollutes the waters, that goes to the water, it changes the biodiversity, etc., etc. So for instance, there are a lot of interest today in monitoring the soil so that you could design your agricultural practice. I'll show you a simple example. This was work that was done while I was at IBM. Second is in soil. There are changes in the global soil and water cycles, carbon cycling, nutrient cycling, and again, matter in soil, that is not very well understood. Then I'll give you an example of water. So let me start with the three. In agriculture, I'll describe to you a project that we did at IBM, and this was a collaboration with a winery in California called Gallo, where we looked at satellite imagery-driven drip irrigation for wine grapes. It's a very clear-cut example that shows you the benefit of this type of monitoring. This was using satellites. Then when I moved to the University of Chicago, we set up what is the first university-based fully buried sensor network. I wanted to show that you could have a buried sensor working according to the concept of the cyberphysical network that I talked about. And this was done mostly with undergraduate students. I wanted to show that it can be very simply put together. It was one postdoc and a group of undergraduate students. And then I'll talk about water monitoring of large bodies of water that we are doing in India, primarily in the Godavari near Rajahmundry and Narsapur, but also now in other places. Now, I am not, and we are not water experts. We are material scientists. We make sensors, we make sensing networks. What I'm trying to find out here is collaborative opportunities with experts in the environment and water. So if you can think of anything interesting that one can do with these techniques, that's what I would be interested in discussing. Let me quickly run you through the example of agriculture. As I said, this is a joint project between IBM and Gallo. And the way wine is cultivated is what they do, something called drip irrigation. How many of you know what is drip irrigation? Okay, good. Most people know. But basically, there's plastic tubes with water with holes in it, and then you deliver the water through the holes, and it seeps through the soil. Now, today, when this drip irrigation is done, it is just turned on, and the farmer, whenever they feel they should do it, they do it, and it's done to the whole field. What we did is we pixelated the drip irrigation by putting valves, etc., so that we can deliver water to 10 by 10 meter approximately pixels of land and vary it that way. What happens is, if you irrigate all of the land in the same way, then some of these regions brown differently or green differently, and then you get uneven harvest and it affects the yield. So very simply put, what we wanted to do was use Landsat satellite data. So this is a satellite that's taking data twice a month approximately from every region on this earth. And using Landsat satellite data, you get images in 11 different wavelengths. We take the images taken on the green and the red, and then using simple formula, we basically look at essentially the chlorophyll content or the greening content. And so we analyze for greening of the field. We combine that with with local climate data, wind speed, relative humidity, etc., etc. We estimate the evapotranspiration from the plant. Okay. And that combined with the greening, we calculate, and this is what the yellow scientists did, we calculate how much water should be sent to a pixel, and this way we minimize the water usage, because in California water is overused, and B, we try to make a uniform product across the field. So this was the experiment. It was done across 2 seasons. So just to show you, these are the, this is a 10-acre plot, so we basically kept valves and created our little pixels. Okay? These are the pixels, water transpiration calculation, basically what I told you. Okay? So this was our trial area where we pixelated it. This is a picture of the whole thing. These are the drip irrigation lines. Typically, there are, let's see. So typically, the water comes down this pipe, and then using a bunch of solenoids, etc., we can reroute it. These are the evapotranspiration equations. I won't go into this, but this is the main result. So we did 2 experiments, right? One is one area we optimized for yield. The other area we optimized for water efficiency, meaning, how much water is used per ton of product or so. And in both cases, over 2 seasons, we found somewhere between 10 to 20% improvement, both in yield and water efficiency. And this was done, just by simple monitoring of satellite data. And this really opened our eyes to what could one do if one actually put sensors in the ground and got much more accurate data, right, to estimate and improve yield. So this was our sort of first exposure to this whole business. Now, we did return of investment calculations as a function of resolution, etc. And basically we found that, this using a technique such as this, you'd get profitability in a few years. Now imagine if we were able to actually put moisture sensors in the ground. It would make it a much more efficient technique. But today, it is not possible to do that. It is too expensive. Okay? And this is for something like grapes. Grapes are a very high value thing, right? Wine grapes. It is about $10,000 US per acre of produce. Even there, sensing technologies today are still expensive. Right? 5 years later, it probably will not be. But we are at that point where this technology is changing rapidly. And you will see this. So this technology is still far away from other crops. Take sugarcane. Sugarcane in India is about roughly $1,000 to $1,500 per acre of produce. And so that's a mid-level crop. And you take something like wheat. I know in the US, in the Midwest, winter wheat is about $60 an acre. So over there, using these types of sensing technologies becomes very impractical, right? So the opportunities are there. The bottleneck here is in essentially reducing the cost of the sensor and the sensing technologies, right? So today you can buy wireless stations for the field. Each station will cost between $700 to $2,000. And you can put it only one every few acres. And A, that it's expensive. B, you want to monitor this data on the scale of 10 to 20 meters because that is the soil variability length scale. And so monitoring it every acre does not give you that much of a benefit. So going back again to the whole matter of detections, in the case of land or soil, on the left column, these are the various things that one wants to detect. And in blue, I've pointed out talking to agronomists, the most important thing that they would like to measure. One is microprecipitation, right? You want to know changes in water over a scale of 10 to 20 meters. That does not exist today. Two, moisture content. There are point moisture sources, but you want to measure moisture averaged over about a meter or so. Because in the point measurement, you get all kinds of variation. There are pockets, etc. in the soil. Temperature of soil surface, and you want nitrate content in the soil. This is the biggest unknown. There is no good nitrate sensor for soil. So this is something in my lab we are working on. If this can be measured accurately and cheaply, I think it completely changes the way we apply fertilizer. Nitrogen is much more volatile, and typically in fertilizers you will add nitrogen, potassium, and phosphorus. Potassium and phosphorus are less volatile. Once you have them, they are there in the soil for years. Nitrogen changes season to season, so you want that more accurate. So now the whole idea, going back to the first page that I've shown, if I get all these measurements and then I can do analytics and combine it with weather data, etc., I can, in the case of agriculture, I can generate a lot of outputs. I can tell you pesticide, process control, recommendations, fertilizer recommendations, irrigation recommendations, seed selection if you combine this with plant genomics, etc. There's a lot of interest in all of this. You can also look at it from a business point of view, right? If you can predict food production, then the finance companies start getting interested, investment companies start getting interested. So this is the example with the agriculture that got us started. Now I will switch gears to the second description, where I will tell you about a buried underground soil sensing network that we established at the University of Chicago campus. So this is the first sort of functioning buried network where even the antenna, the sensor, everything is underneath the ground. So you took your cell phone and you dug a hole in the ground and you covered it up. Do you think you would get a signal? How many think you would get a signal? I took a cell phone and I buried it under the ground, right? You still get some signal if it is shallow enough, because the electromagnetic wave will refract out of the soil. And your cell phone wavelength is right now sort of too short. But if you use something like 900 megahertz, then you can get signals coming down from maybe a foot below the ground, and which is what we've done. It's very important for wireless sensors to have everything buried under the ground, because tillage, surface treatment of the soil, etc., you don't want anything poking out. So we did a wireless network, and then the data all comes on the cloud, exactly the description of the system I talked to you about. Okay. So there are several different wireless networks available today. One of them is called Sigfox. This is a company. It's 900 megahertz. It is low power data, about 12 bytes per packet. Okay, so it's good enough to give you, soil moisture, temperature, etc. data. It is not good for video, but we don't need video. It has long range. For us, we are seeing for buried networks a range of about a mile, mile and a half. You can also use another network called LoRa that is more popular in India, but these networks are coming up. I'll skip this. So when you take a sensor, you need some other electronics. The signal comes in, you need a little processing, you need a little memory, you need a radio, you need an antenna, you need a battery. So we put all this together, okay? And so the sensor comes, then the signal goes out of the ground to the antenna, then we have a pickup antenna at the top of our building. That takes the data and it basically goes through a base station. There's a callback APIs, and then it comes to the web. So we have a website, thoreau.uchicago.edu. All of this data there is there. Our goal here is to have all the data available in public form in a completely open manner. So this is our sensor box. We use standard chips made by TI or Atmel, and we put it together. All of this was done by undergraduate students. They developed the power management. We bought simple commercial sensors for temperature, electrical conductivity, soil moisture, and water potential. And we put them on campus. This is a picture of the University of Chicago. It's a big lake over here called Lake Michigan. This is Lake Drive. This is a place called the Midway Plaisance. So the World Fair in 1890 was held over here. And Swami Vivekananda, I don't know if you know, he gave a famous speech in Chicago. So he came to this World Fair in 1890s. So we learned about that in school in India, and people in Chicago know about the World's Fair even today. And this is a well-known road, and you guys know of the boxer Muhammad Ali. How many of you are young enough to have heard? How many have heard of Muhammad Ali? Raise your hands. Okay, good. So Muhammad Ali used to take his motorcycle and go up and down in the 1960s. Very fast, apparently, on this road. Okay, so this is the Hyde Park campus. This is where the antenna is. This is my building. I sit over there. So these are the sites. So let me see. So what we do is we dig a hole, we put in the sensor, the wireless, everything, and we cover it up. So you see nothing coming out, right? So sometimes it's actually difficult to figure out where the sensor box is. And this is our building. And these are locations of some of the sensors. This is where I live. So one of the boxes is in my backyard. And you can see very interesting things as a function of time. We are collecting this data. You can see how this water retention depends on the type of the soil, etc., which is all expected. These are the kinds of things we get, right? Heat maps over time. Shown here, soil temperature, moisture, water potential, etc. And as you can see, for instance, this is the big Midway Plaisance Road. The cold winds come in from the lake, and this region is usually colder. And you see different effects. So the idea here is that if you can collect this data over time at high resolution, it can tell you a lot about the evolution of soil. As you start collecting more and more information of other species, other variants, this becomes a very powerful technique that nobody has really adopted before. This is some technical stuff which I will jump, where we basically calculate the wireless signal propagation, and all we want to show is that the electromagnetic signal comes and it actually refracts out of the soil. We have done wireless models, and you know, it is expected that you will see transmission of the signal through the soil. We've correlated the signal propagation to the volume water content. It is interesting, when it rains, the refractive index of the soil changes, so the wireless signal strength drops. So by just measuring the wireless signal strength, you can figure out what the soil moisture is. So you start seeing these very interesting cross correlations. I will skip this. This is a wireless communication model. Let me now move to the third topic, which is a larger topic I wanted to discuss today, which is our development of what we call a water-to-cloud platform of monitoring species in chemical species and organic species in large bodies of water. Okay. So this project started with a Gates Foundation funded project in collaboration with the Administrative Staff College of India in Hyderabad, to monitor, in our case, the Godavari River. I had originally been interested in the Ganga, and I was coming here in 2015 talking to people, but then we got an opportunity to start our work on the Godavari. Okay. I use this slide when I give talks in the US, but all of you know more about the Godavari than I do, so I will skim this slide about where it is. But basically, we are doing our measurements in Rajahmundry and in Narsapur. Narsapur is closer to the ocean. Rajahmundry is a little more inland. It's a major railhead. So the things that one wants to measure and one measures are listed over here. I've divided it into three categories. In green are the quantities that are rather easily measurable using an instant sensor. We use a sensor by HANA. So our goal, our technique is the following, right? So we have the river and we have a mobile sensor platform. And we take the mobile sensor platform on a boat. The sensor platform also has GPS. And then the boat goes across the river. It can go along the banks, it can crisscross, and it keeps taking data, and the data is logged to a certain GPS coordinate. So in the end, we can get heat maps plotted against a Google Maps type of picture, showing various sensor parameters as a function of location and a function of time. So we get dynamic heat map data using a mobile sensing platform, right? It's different from putting fixed sensors. Fixed sensor gives you the advantage of 24/7 monitoring, but a mobile sensor, in our case, we run it over here maybe once in 2 weeks, 2 or 3 times in a week. That range typically more like twice a week, but we get data with meter scale resolution. So if I divide these three, there are the green, there are the sensor, there are the parameters that you can easily sense: pH, turbidity, dissolved oxygen, conductivity, total dissolved solids, and nitrate. We use a HANA sensor, and that sensor, mobile sensor, typically costs between $4,000 to $5,000. Again, I keep mentioning the cost because this is the biggest rate limiter today. But these costs will go down. If you look historically, these costs have been going down. Okay? Next, in yellow is a sort of a new family of sensors that are more fluorescence-based. They are more expensive. In this case, we just bought it. We are measuring tryptophan, chlorophyll, and colored dissolved oxidative matter. And this is a sensor by Turner. And this one is more expensive. It's about $15,000, but it allows you to start measuring some of the things related to, organic or bacterial or living matter. Okay? And then in the pink is stuff that it is really very difficult to sense instantly, but you really want to know it, which is biochemical oxygen demand and E. coli. So one of our goals is to try to see if we can get some idea of these two by proxy measurements of all of these parameters, and then combining it with statistical or machine learning techniques, etc. Okay? Using all the power of computing that you can get. So the way we did these are my colleagues, Srinivas and Priyank, and we take a boat, as I said, and the boat has these sensors, and the boat goes up and down, and we measure and we get the heat maps. And I'll show you some interesting results. Again, let me stress, I am not a water expert. Let me show you the data, and then I would really like to hear what you think about it, whether it makes sense, whether there could be interesting experiments we could do. So I'll start with the pH measurements. Rajahmundry is on this bank. And as you can see in this region, we see that the pH is usually high. One of the interesting things we found in the Godavari around Rajahmundry is that the pH varies from about 8.5 to 9.5. It is much higher, it's much more basic, and people did not seem to know about it. Okay? And so we were wondering why. So if I go to a blow up here, see, this is a big paper mill. I think it is one of Southeast Asia's largest paper mills. And along its banks, we usually find that the pH and the electrical conductivity, these two we found are sort of the most useful, quick parameters to look at contamination. Always usually high. Okay? And so it's clear that these guys are dumping something, Most likely it is bleach. You know, bleach will be alkaline, it will increase the pH. So this is what we think it is. So this is the first sort of set of results that got us thinking that maybe we can develop this as a regulatory or a compliance tool, or as you pointed out today, that we could use this to measure volume of effluents, right? If we, which we didn't, which we are going to be doing soon, is that we can measure flow rates of the water, then we can actually calculate the amount of ions that are being dumped over here. Here is an example of electrical conductivity, same thing. Wherever this factory is, we see a peak in the electrical conductivity. If I look at these pictures, it's being dumped most likely somewhere around here. Okay. Same thing where the drains discharge. There's a drain here that discharges Rajamundri's waste, and you know, again, where the drain discharges, we see peaks in the electrical conductivity and the pH. And this one has daily variations. In the evening, generally the discharge is higher than discharge in the morning. Okay. This makes sense. Here's a second example. Now, this is in the Yamuna, okay, north of Delhi station. This is the area called Wazirabad. So there's a barrage over here. And they do some water management here. They open this barrage and then let fresh water in, and then after a week or so, they close it. And we wanted to see the effect of this. Now, this side is Delhi, on the west side, east side farmland. There are 6 drains that drain from here into the Yamuna, right? And in fact, if you go near the Yamuna, you can already smell the sulfur, which tells you the DO is so low that you're getting anaerobic processes going on. So this is the picture here, but these measurements were done by Priyank and Srinivas. So the day after the barrage was opened and fresh water let in this case, the electrical conductivity is low, but you can start seeing that the contamination is coming from the left bank, the west bank, right, from the drains. Now, over time, this contamination increases, and quite soon this becomes a lake, which is contaminated. The effluents diffuse out, and it covers the whole place. We can see the same effect with dissolved oxygen. Same thing here. In fact, dissolved oxygen again peaks in the evening. This is what we see when the household drains and all dump in the evening. Its numbers go up. It becomes a drain. Go down, sorry, yeah. Yeah. So this also got us thinking that this type of dynamic, heat mapping can probably help in designing water management. Again, I'm not an expert in the water management aspects, but we can measure the effects that it can have relatively easily with just this sensor head and a boat. One of the things we want to try to do is automate things and start using water drones instead of boats. Makes the application much more prevalent globally. For instance, in the US, labor costs are so high that it's very difficult to do boat-based experiments. In India, it is more affordable. Then we started making our heat mapping technique a little more sophisticated. We started, crisscrossing the river. We started taking more data and getting sort of more dynamic 2D maps. This is an example from the Narsapur area. And over here, this is the ocean is this way. There are 2 drains over here, and I'll show you results for these 2 drains. This drain dumps 70% of the Narsapur town's refuse in. There is also a solid land waste dump over here, I'll show you. And there is another drain that comes from the right. As you can see, where the drains come in, there are hot spots. You can see that the DO is reduced. And we can see that again in a little more detail. You see, we took the boat and went up this nala or drain, and obviously the DO numbers this case, this is electrical conductivity, I'm sorry, are elevated. But again, the same thing, that we can see hotspots, and if we can measure flow rates, we can probably estimate the amount of effluents being dumped. This is an example of the solid waste dump. The town of Narsapur, just take their stuff, put it by the river. This has been going on for years. And again, if we measure, we can measure the electrical conductivity, and in this case, nitrate. It's very clear that there are hot spots. So the water is leaching the stuff from the solid waste dump, but the Godavari is very rapid over here, very fast moving water. So it gets diluted out pretty quick and then dumped into the ocean. These are some recent measurements that we started doing in the Banaras area. It's the same picture that we are seeing. Again, you see hot spots near Nalas. It's all that's expected. Interestingly, on the 31st January, the morning after the lunar eclipse, there were a lot of bathers in the river, and so the DO numbers really went down compared to other days. It was just an interesting observation that it seemed to be linked to human activity. And now we have, as I said, this new set of sensors. So we've started monitoring CDOM and tryptophan. And again, these numbers also go up where the drains or nalas meet into the river. Again, this is the Banaras area. Same thing with chlorophyll. Well, not really the same thing with chlorophyll. With chlorophyll, what we are seeing is a diurnal variation, and we don't quite very clearly understand this. Srinivas has a model. I'm not sure whether I totally agree with it yet at this point. In general, from the places that we've measured, the Banaras area is relatively clean of E. coli. So is the Godavari. We will be measuring in the Ganga around Bengal. I believe the numbers are much higher over there. So as we've started collecting, the first step of our project, which has been going on for the past year, is to show that you can build this system, you can aggregate the data, you can visualize it, curate it, and this is successful. Now all that is there. If you go to our website, you can find all the data by day, by species. So the process is working, all the infrastructure is there. Next thing we wanted to do is to start doing some machine learning type analysis, as I mentioned, to try to determine parameters that are more difficult to determine. And in this case, we are doing correlation between, say, chemical oxygen demand and CDOM. And we do see a reasonable correlation. This is work in progress. This, you need big data sets for this. So we have like a 6 to 8 month experiment. We've collected data for a few weeks. So all of these results are preliminary at this point. Interestingly, we see correlation between tryptophan and the total and fecal coliform. So the idea here is that if we can measure tryptophan and it gives us some indication that there is a certain high probability that E. coli may be higher, then it may be worthwhile to do a lab-based E. coli measurement at those points. So we want to treat these instantly measurable parameters or sets of parameters as a sort of proxy indicator for these components. So we see correlation for coliform. The only thing you'll notice is that the fecal coliform numbers are rather low here, varying from 4 to 10. I would be much more comfortable if we, check this variation across a much larger range. And this is what we are planning to do, hopefully, with the numbers in Bengal. Same thing we do for chemical oxygen demand, with the predicted value. And here we start measuring things like using temperature, electrical conductivity, turbidity, and trying to get an indication of COD, chemical oxygen demand. So this is work that is just starting out, the machine learning correlation, and this is going to be going on for a while. So in the end, the vision I have is that you'll divide land up into geopixels or water up into pixels, and each of these pixels will contain stacked sort of whole vertical stack of information, right? It could be heavy metals, E. coli, BOD, etc., and then it can be population, soil type, rainfall. Once you start aggregating this, you can use these various vectors of data to develop very interesting models based on physics, chemistry, geology, etc., to predict things, right? For agriculture, for environment, that sort of thing. So this is the big picture goal that we have. Let me quickly switch to a bit about talking about a little bit of the results on sensors and sensing technologies that we've been developing. So now I'm going from the system level back to the device level, as I mentioned to you. The big rate limiting step in all this business is the quality price of the sensors. So two things that we are interested in are, A, sensors for things like E. coli, and B, sensors for, say, soil nitrates, sensors for heavy metals in water. There aren't good sensors for these things. If you look at sensors today, they are either you're basing it based on some electrical output of a transistor. So there's a transistor, there's an electrochemical cell or something, and it has a current flowing, and then you have an analyte and the current changes. And you try to relate the current change to the amount of the analyte. Or you measure something like that's optical, fluorescence or absorption. It's an analyte, it changes the fluorescence. You can tag the analyte with the fluorescer, and you look for light in a certain band of light. The third thing that we are looking at is because you're limited in the resolution, either electrically or optically, just looking at gross fluorescence at a certain wavelength. We're using this new technology called silicon photonics, where in wafer silicon you can build optical structure and you use their coupling on sub-wavelength, scales. And I won't go into the details of this, but you think of, resonating effects going on where you can measure, because of this interference resonance behavior, you can measure refractive index changes of about 10⁻⁵. So the idea is, okay, if I can measure refractive index of 10⁻⁵ on a surface, these are very minute changes. Can I selectively functionalize that surface chemically somehow so that it attracts a certain analyte or a molecule, let's say a big mercury atom, or let's say E. coli, so that if I detect this small change, I can say that with specificity, I can say that it is detecting this particular analyte. So this is the technology we're trying to develop. We built these silicon photonics chips. We see these changes in transmission that allow us to essentially calculate the refractive index changes. This is, nanoscale technology development. These are our ring resonator structures. This diameter is about 60 micron. This spacing is in the tens of nanometers. That's the coupling we're doing. That's the chip. This is our structure. And as you can see, in this case, we are detecting nitrates. If there is nitrates, then there's a shift in this resonance, and we can detect it back. So one is we're using this platform to look at things optically. So for instance, in this case, we find that we are able to measure nitrate concentrations of less than 10 ppm in this case. But the other piece we are doing is the biofunctionalization. We're starting with something like trying to detect E. coli molecules, E. coli microbes rather, and I won't go into the details, but we take a surface. This is SiO2. Then we functionalize it with some NH2 containing compounds, and this then we have antibodies here that then grab the E. coli, and the idea is that the E. coli then we connect it with gold nanoparticles to look at the shift of the wavelength change. So I have a colleague who's a biochemist who's working on that. We have some preliminary results, and these are E. coli that have been fluorescently tagged, and we indeed see that it is being functionalized. And this is now work going on in progress. So I just wanted to give you a rough idea. So I'll conclude with this slide here, which I like to show. This is the Boquilla vine. It's a vine that grows in Chile. And the interesting thing about this vine is that the leaves of this vine assume the shape of the leaves of the plant on which it is growing. This vine cannot see in the classical sense of what we call seeing, but it is doing something with its distributed sensing network that allows it to then adapt and change the shape of its leaves. And this, in my mind, is sort of the earliest form of intelligence. And in the kind of sensing networks that we're trying to develop, I think that is the ultimate goal, that you want to develop a distributed intelligence system that contains a whole end-to-end system, right? So trying to make something like that is the end goal of the technologies that we are all trying to develop. So with that, I'll end my talk. Thank you. Thanks. Please.
So thank you, that's really exciting because we've been struggling with these sensors and for a long time. So the thing that really struck me about the first, your approach, which is I think very different from our approach, and I think this is where maybe there are opportunities for us to work together, is that it seems to me that both with what you're doing with the soil moisture as well as the Godavari and Yamuna pollution detection, it's an approach of let's go and detect everything and then see what relations emerge. And I think because we are an applied research very policy oriented, oftentimes we are starting with the other end saying what are the most critical questions that we desperately need answers for. And I think that synthesizing these two might be a really where the opportunities lie, because in some sense sometimes when you just throw Brazilian sensors into a lake or into a river, and you get what those heat maps. Lake, that's a bad thing, or that's solid waste, And those are things, in a sense, information-wise, it's stuff that we know. But there's other stuff, and I think you discussed some of it this morning. It sounds like it. But there's other stuff which is we don't know how to manage the stuff. And I was wondering whether you think there's, that there are opportunities for us to work together, starting at the other end, saying what is the most important three things we need to know to actually change the system, and then how do we go back and design a sensor network in order to be able to answer.
Yeah, I think what you're saying is absolutely right, and part of the reason we were measuring all these Brazilian things is we don't know so we just we're more interested in setting the system up and saying okay, it's working, but now what use is this? But I think where this can also help is, as I'd mentioned so when you say, okay, these are the three things we'd like to measure, maybe one of those things is very difficult to measure instantly or cheaply. Can you infer it from 12 other things, right? That would be one area. But in the end, I think you want to also zone into only measuring those few things, but using this network to get a distributed sense. What I also talked about with earlier in the morning during discussions was that maybe what the other thing that you guys do is you prefer fixed sensors, right? And with this, right. And the fixed sensors give you the benefit of continuous 24/7 measurement, but at a fixed point. We can't measure 24/7, but we can get high resolution. Perhaps a combination of the two, where you use the fixed place as your reference point, and you can use its variation and combine the spatial variation numbers that we get once, twice a week maybe. But you can get a much more powerful information if you just mathematically couple these two. So I think that becomes really powerful. Say that again? Microcontroller. So we use a TI boards. I can, if you email me, I can give you the specific model details. I'm happy to do that. Say that again. For the sensor data, right? All the measurements that we did is for the sensor data. No. The calculations are, any calculations we did are done later. You know, aggregating, looking at the data, aggregating it. Not in situ, meaning, you know, there's something called at-node computation where people talk about having a sensor and a computer right next to it that does some of the calculation right on the site. That we don't do. This is for the water, or yeah. So in Rajahmundry and Narsapur, we are taking data about twice a week, 2 to 3 times a week. The other stuff, you know, Yamuna was not that much. We've measured it twice. Banaras has been once, but we'll be doing more. And what we do is, so we have these 2 sensor heads, and so we're measuring maybe 10 parameters all at the same time along with GPS location. So you get this Excel spreadsheet, right, of GPS and maybe 8, 9, 10 parameters. And then we just plot them. Yeah, it's a sensor platform, and then you can attach different sensor heads to it. So we have 2 sensor platforms, a HANA sensor, which will carry 5 or 6 heads. They're all connected, right? So all of them are in the water at the same time. And the same thing with the Turner. Turner is 3 sensors.
So like the map which shows about the combination in the modified parameters. So that whole location one is sensed with one sensor.
One sensor head. So a sensor head is like a little package that can handle 5 sensors. So 5 parameters measured in 1 unit. Right? When I'm saying sensor, meaning it's sensing only one thing, right? So 5 sensors, 5 different sensors connected to 1 unit. Between locations, it's extrapolating, yeah. And that distance is few meters to few tens of meters. But yeah, linear extrapolating. Yeah.
I think I have a follow-up question, because I think when I'm thinking of Priyanka's work on the historiography, for example, when you're released from these industries or whatever is episodic, then how do you know you're not just kind of following the same? Because you kind of showed it as one day, which kind of assumes it's a perfect snapshot. And there's a sort of implied things, an implied unstated assumption there, which is, you know, that you're actually capturing a snapshot. But actually the boat takes time, right? So how do you know you're not just kind of following the same, you know, the same molecule basically downstream?
Oh, that, well, it would depend on how you're, you know, on the release statistics and the release time frame, right? That there is episodic releases. This is a good point, right? And we have no way of figuring that out.
Also, you had the Godavari, you said very fast at Narsapur. If you went upstream,
right,
going downstream, then the chances of reading the same molecule are pretty low.
Pretty low, right. We went around and we find that, you know, near the paper mill, there is a zone, right? Whenever we go, there is a zone. It kind of tells us that maybe there is some, you know, continuous stuff going on, right? We absolutely, yeah. This is where I think if you have a fixed and dynamic, then you can, I think, mathematically very accurately say at any given time, you can say how things are. You need a few, you need at least one. This is a very important point that I hadn't realized till now, that you want to figure that out.
we are scientists from agriculture university, but we are sensors in water management, especially the soil moisture sensors. The sensors which you have mentioned in the vineyard, okay, whether they were tested for different site mix, because we are also working with Infosys and also so many engineering college, we have a collaboration and doing a lot of work to develop sensitive sensors actually. And the precisions we are not getting with the varied site. Okay, because there are so many other elements are also interfering with the moisture values. Or whether those sensors have tested there.
So the sensors, so as I told you, so here we were more interested in setting up the network. We bought commercial sensors. Those commercial sensors, they will give you, they claim they will give you the soil moisture data irrespective of soil type. You can also combine it with volume water content. So we haven't really verified that. I took it for granted. This is what they're specifying, this is what they'll do, right? I think also importantly for soil moisture, if you can figure a way of measuring averaging over a meter, that is more powerful than a point measurement. Okay.
That's all right. Right. Point is, actually we have different kinds of sites. There is a lot of heterogeneity in the site.
Oh yeah.
One is clay site, one is sandy loam. We have different kinds of sites.
Right.
And the element, the chemical elements associated with those site types are varying. They are also interfering with our measurements.
But are you developing a new sensor technique or?
No, that sensor whether they have tested for different site types of this.
This I haven't asked them, but they are selling me a calibrated product, and I'm just using it as per their specifications. Now maybe their numbers will change if I have different ions. I'm sure they will change. But I did not look into those details. But as a soil type, the water retention is very clearly it changes like I showed. Yeah. For what? Which ranges? You mean in those rivers?
Those are the agriculture fields. They are land holdings.
Right.
In India, like it's not large areas. We are collecting a sample.
Right. See, I have not thought about it. Right. I mean, in a small river, very fast flowing, it is going to be very different dynamics. And it's a good point. Well, from the wireless point of view, it should be okay because you just put your antenna on top of the mountain. Okay, so you're talking about the wireless link. The sensors, so if it's soil, let us say it's soil, it depends on how high the mountain is, because then you will get the what is called multipath interference. You'll have to look at the topography. I think it still should be okay because we are doing it in a city with tall buildings and so on. We're still doing fine. I don't think it will be a critical problem. I think I'll be happy to discuss this with you. If you can give me some better idea of the topography, how high is a mountain, how far, then I don't think it'll be a serious issue. It's a very good point. So we were not measuring flow velocity. This time when I came to India, I actually brought some flow velocity measurement equipment. So we are going to be starting to measure it because we want to now start estimating total number of effluents. Came here?
Yeah, no, that's vineyard. That's slow down.
Say that again? Vineyard. Yeah, paper has been submitted for publication and it is under the review process. So I'll be happy to send. Yeah. How to handle what? Cloud cover. Okay, so with Landsat, cloud cover is a problem, right? In real life, while you get data twice a week, generally statistically we've seen you get effective data only about twice a month you get actual data, but really because of cloud cover issues, you only can maybe once a month you can get. In Bangalore, how much? Once in 3 months. So this is nothing we can do about it. I don't know. Are there other satellites in the Indian region? Any Indian satellites or? Okay. Sentinel. Which is the European one? There's a new European satellite. That's Sentinel, right? So that is also giving. Are you using that data? Okay. 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 So this is a problem with satellite data, right? We use Landsat because the resolution is good. Green for NDVI, yeah. Can you get green and red in the Sentinel? No? No. I see.
But for a
What is
small
full
area,
resolution in Landsat? In California is not full resolution in India.
I see. So Landsat, I
30
think
meters.
30 meters. And in India, what do you get?
No, I'm saying 30 meters may not be good enough resolution in the Indian.
lot sizes are very small.
That's true. That's right. That's right.
That's right.
That's right. You know, you can buy much higher resolution, but that is not in the green and red and all that. You don't get all that, right? No, you don't get that.
But for the small area, can't you? I mean, that's a relatively small area that you're soil moisture.
10 by 10 meters.
Yeah.
10 by.
You can't just use a drone or just something.
You can. So actually, for us, ours was 10 by 10, but then we were like expanding it to match the 30 by 30. You can do drones, and you'll get much better data. But there's a cost, expense and all goes up, right?
But that cost is going down.
That will go down,
You'll never have clouds under it.
right? That will, and you'll get much better resolution data also. So that will, whenever that comes, that will come. I think if it comes, it will come in agricultural lands first. Is there any problem with using drones in India from the regulatory point of view?
Well, I think
You need special permission or?
but people use it for weddings. Correct. So that's the right.
Range is also.
Okay.
Any questions?
Thank you. Thanks. Yeah. And send me email and what are you work here or are you a student? Okay, what do you work on? Oh, very nice. I should talk to you. So you are expert in remote sensing? Okay. Yeah, please write to me because we are looking to work with someone in this.
I try to work on that sensor jack temperature recording and sending.
Okay. So yes, please send me your email. Just in the subject, just say ATREE or something, then it will. Thank you.
Ramesh here. I am
Hi,
working on
Ramesh.
4th paradigm issue. So we get data analytics at everything.
Okay, okay.
So actually we are working on some Himalayan projects, river revegetation, and Aqua. So we want this type of sensors because project is set to start.
And what do you want to say?
We want to actually monitor how process water budget. And another thing is we want the quality of the water from the origin to the downstream.
Downstream up to origin meaning where?
Origin means when it's from the places,
Right.
the solar.
Right. And then downstream to where is your
Up
downstream?
to Rishikesh, that area.
Rishikesh. Oh, very nice.